Hey everyone, super excited to host now officially competitions Grandmaster Nischay. It's been a long time coming, but I've been teasing him about it for a long time. If you know, you know. We're celebrating his win and also new feat where he's broken into top 10 rankings globally. Nischay is now ranked 7, and he did that by winning the RSNA, the latest RSNA competition with Team Oxygen. Nischay, double congratulations to you. Actually, triple because we didn't celebrate the competitions one.
Thanks, and yeah, feels good to be in top 10. Yeah, finally.
Did you get the hoodie?
Not yet. I guess I need to come to your home to steal it someday, but yeah.
Let's see. Awesome. So this video for everyone watching is an overview of Nishay's solution. In this video, he'll be presenting you through his solution, his team solution, and we'll try to understand that. I'll be the dumb audience and I'll try to ask any questions wherever. But with that, Nishay, I hand it to you.
So yeah, hi everyone. This is Nischay, and I'm representing Team Oxygen. And my other teammates was Harshit and our other colleague Kushinha. So we participated in the competition hosted by RSNA this year, and we placed first in the private leaderboard. So yeah, with this, I also believe this was the formation of Team Oxygen for us, which is nothing but just a similar name to Team Hydrogen, which consists of another three colleagues of us from H2O. Coming on to the summary of our solution, our final solution basically consists of several models trained on diverse settings, and our solution could be considered as a two-stage architecture because in the first stage we were just doing the segmentation part using a 3D segmentation model from which we basically extracted the mask and the cropped images from that, and then we use those data set into our stage 2 models, which basically consist of a 2.5D, or you can also consider it as a 2D CNN based approach. And we also use several RNN solutions for training our stage 2 models. Then coming on to a major factor which led to us winning the competition was auxiliary loss. So what we did was, while fine tuning our stage 2 models, what we did was we basically used an additional segmentation decoder head, which was basically predicting the mask for us, and then we were using those predictions as well to use for another loss, which was a dice loss for calculating the segmentation loss, and then this basically led to a better generalized model for our solution. Then I believe one of the more key factor which led us to a victory was using the diverse input data, or in the diverse pre-processing of the data set. So we basically use two different types of pre-processing, which I will maybe explain in the later part of the slides. Then the training time which was required for training our models was around 2 to 3 hours per GPU, and around it took around 6 hours for the stage one model, so the 3D segmentation models to train. Yeah, so talking about the pre-processing, I think it was quite basic and straightforward. At the beginning, like we were converting the DICOM files to the NumPy volumes, and then we were also converting the data into different scalings. But the major difference between the two pre-processing which we used was, one of them was based on the Theo Wheel's idea, which he shared in the public forum, which was to standardize the data first and then sort out the G positions slices. And the other pre-processing which we did was based on my rescaling and our own pre-processing, which was basically using soft tissue windowing in the volumes, within the volumes. Then I believe the split was quite simple. We were doing group K fold on patients, so we had different patients and we did not want any leakage between them. So what we did was we kept all the patients in the same patients in the same fold. So that is why we use group K fold. Then talking about the labels to train our second stage models, we didn't actually use the hard labels or the true binary targets which were given to us for each organ. Instead of that, what we did was we generated the soft labels through them by simply calculating the size of organs which are present in a particular slice, and then simply multiplying them with the original binary targets. So that is how we were able to come up with a different labels which made our models learn better through them. So then coming on to the augmentations, I don't believe we use something extraordinary, and rather we just relied on very basic augmentations for training our models because those were the ones which were performing decent for us. So in the stage one, while training our 3D segmentation model, we did not use any augmentations at all. But for second stage, we use some basic ones like horizontal flip or vertical flip or maybe some rotation based augmentations, while any high augmentations or heavy augmentations or rather any pair of larger augmentations did not work for us, so we just tried to keep them quite simple. And this is, I believe, the overall architecture of solutions look like. So basically, first we have a 3D volume or a 3D images which consist of another axis. You can just simply consider it as a image, but with another g-axis which consists of several images into a sequential manner. So what we did was we first applied our pre-processing, which mainly involves the windowing and the rescaling part. Then the generated volume or the volume numpy arrays were then sent into the 3D segmentation model which we trained. And out of that 3D segmentation model, we simply generated the crops and the masks out of it, which you could see here. And the resolution at which these models were trained was 128 cross 128 cross 128, where the first dimension denotes the number of slices and the other two dimension basically denotes the height and width simply. Then these volumes were passed into another pre-processing step while we were loading the data for second stage model. So what we did was we basically extracted 96 pairs of equidistant slices using the output generated from the 3D segmentation model. So with this, we basically get the cropped slices or the cropped images out of the volume, and they will always be numbered as 96. So basically, it was just equidistant in nature. And then out of those now 96, what we did was we did another split within them. What we did was we took the adjacent slices and convert them into a 3 channel data set. So with that, our sequence length is now left with 32, and now we have 3 channels which are basically through the adjacent slices which we were using. So after that, this is how the feature map or the feature images looks like. So the shape which we are passing now into the 2.5D approach or the second stage model is now batch size cross 32, which is sequence length, cross 3, which is number of channels, cross 384, cross 384, which is again height and width. So once this data is passed into a 2D CNN based encoder, it generates some sort of feature maps for us, which we mainly use for any sort of decoder task which we want to apply. So for that, we either use a segmentation head. This was used just to find out the auxiliary loss and it was only used for the training purpose, while the other main head for us was the classification head, in which we were first using bidirectional grus for gaining some sequential information out of the feature maps, and then we were simply using few dense layers along with the sigmoid activation to finally generate the predictions for us. Then again, some more information about the multi-stage training is that firstly we were using the cropped images which were generated from the 3D segmentation model, and the auxiliary loss which was generated using the mask which we generated from the 3D segmentation model again. Again, this strategy helped us to get a good amount of boost, and you could clearly see it improved around 5% for us in both cross validation as well as on the leaderboard scores, which is like a huge differentiator. Then the 3D segmentation model, I forgot to mention, it was actually based out of the ResNet 18 network. So it wasn't a really heavy network, I would say, because it has just few layers. Then the only external data which we used throughout the competition was the total segmented data set, which is completely open sourced, and we use that to basically pre-train our 3D segmentation models. Then coming on to the stage two models, I will go into a bit more depth. So this is how the architecture looks like for the simple 2.5D approach which we use. So basically, again, the image data is passed, and this particular example is for the efficient net based backbone. So we took out the feature maps which were generated from the output of fifth block and the sixth block of the encoder, and used those feature maps into the segmentation head. So again, the segmentation head could either be a unit based architecture, or in a simple form it could be just few layers of 2D CNN network. And the output of the segmentation head was used along with the masks which were true masks generated from the 3D segmentation model, and through that we were finding out the dice loss. Meanwhile, again, we are also using the classification head because the task for us was to predict the whether there is any injury in a particular organ or not, so it requires some sort of classification predictions as well. So for that we were again finding out the sigmoid predictions and using the binary cross entropy loss to back propagate with the loss. So the predictions which were we were getting was in the shape of base size cross 32. Again, 32 is the sequence length which I mentioned, and NC basically denotes the number of classes which we were using. So again, but in the submission we had to only give just one prediction for a single patient and not 32. So for that we simply applied a maximum aggregation method to find out the prediction which have the maximum confidence from the model, and we simply use those predictions for our final solution. Then this is how our final ensemble looks like. So again, one thing I should have mentioned was we used two different type of models. One was specifically trained for the extravasation and bowel organs, while some models were trained for all organs, I believe, and that doesn't include any extravasation organ labels. So these were few of the models which we used. On the left side, you could see are the ones which are based on our pre-processed dataset, and on the right are the models which were basically trained using the Theo's pre-processing. So, and the numbers which are shown here basically denotes the weights which were given to the particular model. So at the first step which we were doing was we were doing slice level ensemble, so basically the ensemble between the sequences as well, and then we do the maximum aggregation based on our models and based on the models which were trained using Theo's pre-processing. And then again the maximum aggregation, after the maximum aggregation we were again doing another weighted blend to get the final predictions for us. Similarly, for the ensemble of extravasation and bowel models, we again used few models which were based on our preprocessing and few models which were based on Theo's preprocessing. Again, the strategy for the ensemble was quite similar. The only difference was during the training part. So the solution consists of 8 models which were based on different architectures. So we used 1 quart light medium and 4 quart light small and 3 efficient net V2S for extravasation. So I've mentioned this earlier. We assembled around 17 models for the all organs and around 8 models for the extravasation. So these were the only architectures which we used, and for the decoder part, we were mainly relying on the GRUs because they were working better for a smaller sequence length. Some of the important findings or the interesting findings which I believe we found out earlier in the competition and helped us were basically we figured out that training the models for extravasation along with the other organs wasn't performing so well. The reason was we were generating the masks and the cropped images from the stage 1 3D segmentation model, but the 3D segmentation model wasn't performing so well for the extravasation, so it wasn't so meaningful to basically train extravasation organ on the cropped images. So we kept this particular organ for another training. So the all organ models were trained on the cropped images while the extravasation models were trained on the uncropped images. That was the major difference in our training part. Then again, cropping down the slices was one of the most important factor to make our models learn and focus better on the part of the image where there is a high chance of an injury. Then talking about loss, I think we simply took the problem as a we simply trained our models using BC loss rather than a cross entropy loss, and treated the whole problem as a multi-level classification rather than a multi-class classification. Then I believe 2.5D approach, or rather 2D plus 2D CNNs plus RNN approach. So that was also another thing which helped us in the competition, and I believe was another interesting finding. Then again, like, we trained many models on full data training, which you could see. So this basically involves training our models on the entire 100% data set which was given to us, rather than using the k folds. So as you could see in our ensembles as well, there are few models which I have mentioned full data. So these models were basically trained on the entire training data set, and there was no validation done for them. But this gave us some good amount of boost in the leaderboard, so we proceeded with them in the ensemble. Then these again are the few techniques which gave us quite consistent boost throughout the competition. So again, the crop level within the study, then using the auxiliary head, and the third one is quite interesting. So we used several coat light models which were recently published, and these are basically quite stable for this. These performed quite stable for us throughout the competition. And like, by stable I actually mean that they were converging at the very last epoch and were always quite stable with the loss. We never got any nan errors or unstable training during the fine tuning of these models. So we are quite heavily using code light models in this competition. Then again, creating the soft labels by multiplying the binary labels which were given to us by the host along with the organ size was another good idea, which I believe worked well for us. And at the end, for the post processing, we didn't do anything hard post processing, but just a simple scaling of the predictions towards the injuries. So that was the only post processing which we did, and the scaling factors which we used were based on the cross validation score which we were getting. Yeah, so I think a simple model, I could just define a model which you could have trained, and it's just a single model which could actually get you a top three rank using just a single model. So architecture, you may use the code light medium, and training of stage one could be the same as we used, which was 3D ResNet structure. And for training the stage two models, you could simply train some full data models using code light medium and some random seeds. So I believe this solution is capable of getting you a top three rank in the private leaderboard as well. So we proceeded with that, and I believe this could be a much more simpler and efficient solution to be used anywhere. I think that was it from the presentation part, and this was mainly a solution. So I believe I've covered most of it, and yeah.